There's something unsettling about looking up at the night sky and realizing we barely understand the rules of the universe we live in. Picture this every second. Galaxies are racing away from each other faster than light should allow, stretched apart by an invisible force we call dark energy. Scientists can measure its effects, but no one can explain why it exists or where it comes from. It's as if the cosmos is playing by a hidden set of rules, and we're only now beginning to decipher them. This isn't just a minor gap in our knowledge, it's a cosmic-sized mystery that shakes the very foundation of physics. Now, think about gravity for a moment. We're taught it's the force that keeps our feet on the ground, but what if it's just one thread in a much larger tapestry? Imagine gravity as a cosmic puppet master, tugging planets and stars into orbit, while unseen forces, dark matter, quantum fields, even extra dimensions pull the strings from behind the curtain. The universe isn't just stranger than we thought, it's stranger than we can think, and that's where things get fascinating. In this video, we're diving into 30 of the most mind-bending theories about these hidden forces shaping reality itself. From the possibility that we're living in a hologram to the idea that dark energy could be the breath of a higher dimensional being, these aren't just wild guesses, they're serious scientific explorations at the edge of human understanding. Some might sound like science fiction, but each one is a clue in the greatest detective story of all time, the hunt for the universe's deepest secrets. So, if you've ever wondered what's really out there, lurking beyond the edges of our equations, you're in the right place. Let's begin. One of the most startling ideas in modern cosmology suggests that dark energy, the mysterious force accelerating the universe's expansion, might not come from some distant, exotic source, but from the very fabric of space itself. Think about the quantum vacuum, the so-called empty space between stars and galaxies. It turns out it's anything but empty. At the tiniest scales, particles and antiparticles constantly flicker in and out of existence, borrowing energy from the universe in fleeting bursts. These quantum fluctuations create a seething ocean of energy, and some scientists believe this could be the hidden engine behind dark energy. Here's where it gets even weirder. When physicists calculate how much energy these quantum fluctuations should produce, the numbers are mind-bendingly huge, around 10 to the power of 120 times stronger than what we actually observe. This glaring mismatch, known as the cosmological constant problem, has been called the worst theoretical prediction in the history of physics. If the math were right, the universe should have ripped itself apart moments after the Big Bang. Yet here we are, in a cosmos that's expanding at just the right pace for galaxies, planets, and life to exist. So how do we reconcile this colossal discrepancy? One intriguing possibility is that these quantum fluctuations cancel themselves out in ways we don't yet understand. Maybe there's a hidden symmetry or an undiscovered law of physics that keeps their energy in check, leaving just a faint residual effect. The exact amount needed to explain dark energy's gentle push on the cosmos. Others speculate that our universe is just one bubble in a vast multiverse, where most bubbles do tear themselves apart instantly, and we simply live in the rare one where the numbers lined up perfectly. This isn't just abstract theorizing. If dark energy truly comes from quantum vacuum fluctuations, it would mean the universe is shaped by an invisible, ever-present hum of energy, a background whisper driving galaxies apart while remaining undetectable in our labs. It would also mean that the greatest mystery in cosmology might be hiding in plain sight, woven into the empty space around us, and that raises an even deeper question. If we're only sensing the faintest echo of this quantum sea, what else might be lurking just beneath our perception? The quantum fluctuation explanation for dark energy is elegant in theory, but it's far from perfect. One of the biggest hurdles is something physicists call the renormalization problem, a fancy way of saying the math gives answers that are quite literally infinite. When you try to calculate the energy of these quantum fluctuations, the equations explode into impossibly large numbers unless you artificially cancel out the infinities with workarounds. It's like trying to measure the weight of an ocean by counting every drop of water, only to realize your scale keeps breaking because the numbers are too vast to handle. This isn't just a technical hiccup, it suggests we're missing something fundamental about how gravity and quantum mechanics interact. That's why some scientists have turned to a completely different idea: quintessence. Imagine dark energy isn't a static force woven into space itself, but something more fluid, a dynamic field that changes over time like a cosmic weather system. Quintessence proposes that dark energy could be the work of an undiscovered particle or field, one that evolves as the universe expands. Picture a balloon inflating, but instead of blowing into it at a steady pace, you sometimes press harder, sometimes ease up. That's quintessence in action, a force that might have been weaker in the early universe, stronger now, and could shift again in the future. What makes this theory so appealing is how it could solve another cosmic puzzle, the coincidence problem. Right now, dark energy and matter's densities are oddly similar in magnitude, as if balanced on a knife's edge. If dark energy were static, this would be a bizarre fluke. But if it's dynamic, that balance might just be a temporary phase in a much longer cosmic story. Some models even suggest quintessence could eventually fade away, leaving the universe to collapse under gravity or rip itself apart faster than ever. Of course, quintessence has its own mysteries. No one's detected this hypothetical field yet, and it requires fine-tuning to match observations. But that's the point. These competing theories remind us that dark energy might not be one monolithic enigma, but a signpost pointing to deeper layers of reality we've barely begun to explore. Whether it's quantum foam or a shifting field, each idea pushes us closer to answering the ultimate question: what invisible hand is writing the rules of our universe? But what if the mystery of dark matter isn't about missing matter at all? What if we've been looking at gravity the wrong way this whole time? That's the radical premise of modified Newtonian dynamics, or MOND, a theory that dares to rewrite the rules of gravity itself. Instead of invoking invisible particles to explain why galaxies spin faster than Newton's laws predict, MOND suggests that gravity behaves differently when it's extremely weak, like at the edges of galaxies where stars barely tug on one another. Picture a car that inexplicably speeds up when you take your foot off the gas. Newtonian physics says that's impossible unless there's hidden fuel in the tank. MOND, on the other hand, proposes the car's engine just works differently at low speeds. The idea first gained traction in the 1980s when astronomer Mordechai Milgrom noticed something peculiar. If you tweak Newton's equations just slightly for extremely gentle accelerations around 100 billion times weaker than Earth's gravity, galaxies suddenly rotated exactly as observed, no dark matter required. It was as if the universe had a speed limit sign no one had noticed before, whispering to stars at the fringes of galaxies, "Move faster than Newton says you should." But MOND isn't without its critics. Take the Bullet Cluster, two colliding galaxies where X-ray observations revealed most ordinary matter got stuck in the middle, while gravitational lensing showed the bulk of the cluster's mass had sailed right through exactly what you'd expect if dark matter were real. MOND struggled to explain this without some form of invisible mass, forcing its proponents to get creative. Some introduced relativistic extensions like TVS, blending MOND with Einstein's theory of relativity to account for these extreme cosmic events. Others suggested that even MOND might need some dark matter, just far less than standard models claim. What makes MOND so compelling despite the hurdles is its audacity. It challenges us to question whether we've been too quick to invent new substances to patch over gaps in our understanding. After all, science has rewritten the rules before Einstein showed Newton wasn't the final word on gravity, and quantum mechanics revealed a world where particles defy classical logic. Could MOND be another chapter in that story, or is it a dead end? The answer might lie in the faintest gravitational tugs between distant stars, waiting to reveal whether our universe plays by familiar rules or ones we've yet to fully imagine. Now, let's shift our gaze to a different kind of cosmic detective story, one that hinges not on rewriting gravity's rules, but on an invisible sea of ghostly particles so light they barely register as matter at all. Meet the axion, a hypothetical speck of existence predicted not by astronomy, but by the esoteric math of quantum chromodynamics, the theory governing how quarks and gluons bind together. These particles were first dreamed up in the late 1970s to solve an entirely unrelated puzzle: why the neutron's electric field stays perfectly balanced when theory says it shouldn't. But here's the twist: axions, if they exist, might also be the secret ingredient of dark matter. What makes axions so unusual is how little they resemble the traditional image of matter. Imagine a particle so feather-light that trillions could pass through your body every second without a trace, each weighing less than a billionth of an electron. Unlike bulky dark matter candidates, axions wouldn't lumber through space like cosmic boulders. They'd behave more like waves, overlapping and interfering in a quantum dance that fills galaxies with an ethereal, rippling fog. Physicists call this fuzzy dark matter, and it could explain why small galaxies don't show the dense, clumpy dark matter cores our models predict. Instead of collapsing into tight knots, axion waves would naturally smear out, creating halos so diffuse they'd barely disturb the stars passing through. The hunt for these phantoms is already underway. Deep underground, experiments like the Axion Dark Matter experiment, ADMX for short, tune massive magnetic cavities to frequencies where axions might reveal themselves. Here's how it works. If axions exist, they should occasionally convert into faint microwave photons when exposed to strong magnetic fields. ADMX acts like a cosmic radio, scanning one frequency after another, listening for the faintest whisper of an axion signal. So far, the airwaves have stayed silent, but every ruled-out frequency brings us closer to either a discovery or a rethink. And the implications: if axions are real, they'd rewrite dark matter's story entirely. Picture a universe where the invisible scaffolding holding galaxies together isn't made of sluggish, cold particles, but of an ultra-light quantum mist shimmering just beyond our perception. It's a reminder that sometimes the answers to the cosmos' biggest mysteries don't come from looking harder, but from learning to see in a whole new way. What if dark matter isn't made of exotic particles or quantum waves, but of ancient cosmic trapdoors lurking in the shadows of the universe? That's the daring premise behind primordial black holes, remnants of the Big Bang so old they might predate stars, galaxies, even light itself. Imagine the universe in its first chaotic second, a seething broth of energy and pressure. In some regions, density fluctuations could have been so extreme that space-time crumbled under its own weight, pinching off into tiny, ultra-dense knots. These wouldn't be the black holes we know today, forged in the death throes of massive stars. These would be relics from creation, scattered across the cosmos like invisible landmines left over from the universe's birth. The idea isn't new. Stephen Hawking and others toyed with it in the 1970s, but it gained unexpected traction in 2016 when LIGO detected gravitational waves from merging black holes. The kicker: those black holes were curiously heavy, between 20 and 50 solar masses, a range that doesn't quite fit our models of stellar collapse. Could they have been primordial, born not from dying stars but from the violence of the early universe? Suddenly, an old theory had fresh teeth. If PBHs exist in just the right numbers, they could account for all the missing mass we attribute to dark matter. No new particles required. But there's a catch: black holes, even primordial ones, aren't entirely invisible. When one passes between us and a distant star, its gravity bends the starlight like a lens, briefly magnifying the star's brightness, an effect called microlensing. For decades, surveys like EROS and OGLE have scanned millions of stars, searching for these telltale flashes. Their findings put strict limits on how many PBHs could exist, especially in the mass range of planets or stars. Too many, and we'd see far more lensing events than we do. Yet there's a tantalizing window where PBHs could still hide between the mass of an asteroid and a small moon. In this sweet spot around the mass of a large mountain, primordial black holes would be too light to lens stars noticeably, yet too heavy to evaporate via Hawking radiation, a process that would have destroyed smaller PBHs by now. It's a Goldilocks zone where these ancient ghosts could persist undetected, drifting through galaxies in vast numbers. The implications are staggering. If PBHs are dark matter, they'd weave through the cosmos like invisible threads, their gravity sculpting galaxies while remaining utterly dark. They might even solve another puzzle: the mysterious seeds that allowed supermassive black holes to form so quickly in the young universe. But the hunt is far from over. New telescopes like the Vera Rubin Observatory could uncover PBHs by spotting their rare, subtle disruptions. Until then, the question lingers: is dark matter hiding in plain sight, masquerading as fossils from the dawn of time? Imagine if everything you see, the stars, the trees, even your own hands, were nothing more than a breathtaking illusion, like a shadow cast on a cave wall. That's the heart of the holographic principle, a theory so radical it suggests our three-dimensional universe might be a projection from a two-dimensional surface at its edge. Think of it like a cosmic version of a credit card hologram. The shimmering 3D image isn't really there, it's encoded on a flat, microscopic film. If this idea holds, reality as we know it could be the universe's ultimate magic trick, with every event, every particle, just data written on a distant, invisible boundary. This isn't just philosophical musing, it emerged from the fiery math of black holes. In the 1970s, physicist Jacob Bekenstein discovered something astonishing: a black hole's entropy, a measure of its chaos or information content, doesn't scale with its volume but with its surface area. Later, Stephen Hawking refined this, showing that black holes emit radiation and slowly evaporate, raising a paradox. If a black hole vanishes, what happens to all the information it swallowed? The holographic principle offered a solution. The information isn't lost inside the hole but smeared across its event horizon like code on a cosmic hard drive. In other words, the 3D chaos inside a black hole could be perfectly described by 2D data on its surface. But how could this apply to the entire universe? Enter the add S/CFT correspondence, a groundbreaking idea from string theory. It proposes a mathematical equivalence between a higher dimensional space, like our universe, and a lower dimensional theory operating on its boundary. Picture a sphere enclosing a room. Everything happening inside the room could, in theory, be translated into interactions on the sphere's surface. If true, our 3D cosmos might be a projection of quantum fields living on a distant 2D shell we'll never see. What makes this more than just abstract math is how it could solve the greatest rift in physics, uniting gravity with quantum mechanics. In the holographic universe, gravity wouldn't be a fundamental force but an emergent effect, like how the sensation of wetness emerges from countless water molecules. At the smallest scales, space-time itself might pixelate, revealing a granular structure hidden beneath the smooth continuum we perceive. A digital universe masquerading as analog. Critics argue this is a mathematical metaphor taken too literally, but supporters point to real-world tests. Fermilab's holometer experiment, for instance, hunted for quantum fuzz in space-time by firing lasers down perpendicular tunnels, searching for minute holographic noise. So far, no dice, but the search continues. Whether the holographic principle holds or not, it forces us to confront a humbling possibility. The most solid truths of our existence might be nothing more than shadows dancing on the walls of reality. What if gravity isn't a fundamental force at all, but something that emerges from the chaotic churn of information in the universe, like how temperature arises from the jostling of atoms? That's the radical proposition of physicist Eric Verland's theory of emergent gravity, which turns our understanding of the cosmos inside out. Forget Newton's apple or Einstein's warped space-time. Verland suggests gravity is more like a cosmic mirage, a side effect of the universe's relentless drive toward disorder. Think of it this way: when you blow on a cup of hot tea, the steam doesn't rise because of some invisible steam force. It's the collective behavior of countless water molecules escaping the liquid. Similarly, Verland argues gravity isn't a standalone force but the macroscopic outcome of microscopic quantum interactions we can't yet see. At its core, his idea hinges on entropy, a measure of chaos or lost information. Just as heat emerges from particles in motion, gravity might emerge from the way information rearranges itself at the deepest level of reality, like cosmic Tetris blocks settling into place. The implications are staggering. If Verland is right, dark matter might not be missing matter at all, but a mathematical illusion. His equations suggest that the extra gravity we attribute to dark matter in galaxies could just be an entropic effect, a kind of drag caused by the way space itself stores information. Picture a river flowing faster at its center. You might assume there's an invisible current pushing it, when really, it's just the water's natural motion. In galaxies, Verland's math predicts the same observed rotations without invoking dark matter, a tantalizing possibility. But here's the catch: emergent gravity struggles to explain the behavior of galaxy clusters, where visible matter alone can't account for the gravitational glue holding them together. Critics point to the bullet cluster again, where colliding galaxies left their gas behind like cosmic breadcrumbs, yet the bulk of the mass, revealed by gravitational lensing, sailed ahead. If gravity were purely emergent, how could this separation occur? Verland's supporters counter that his theory is still young and refinements might bridge the gap. After all, even Einstein's relativity needed decades to be tested fully. The boldest claim of all: if gravity emerges from information, then space-time itself might be a kind of holographic scaffold, built from quantum bits we don't yet understand. It's a vision where the universe isn't just governed by laws, but is the laws a dynamic, ever-changing computation where every particle, every force, is just information in disguise. Whether Verland's theory holds up or not, it forces us to ask, what if the forces we take as fundamental are just the universe's way of keeping track of itself? And if that's true, what other illusions might we be mistaking for reality? Time crystals sound like something ripped from the pages of a sci-fi novel, structures that pulse and repeat in perfect rhythm, not because they're powered by energy, but because it's their natural, lowest energy state. Nobel laureate Frank Wilczek first proposed this bizarre concept in 2012, imagining a form of matter that breaks time's symmetry, the idea that the laws of physics look the same whether time runs forward or backward. Think of a diamond that doesn't just sit inert on a table, but constantly flips its atomic arrangement every few seconds, like a cosmic metronome ticking forever without batteries. What makes time crystals so revolutionary is how they defy our deepest assumptions about equilibrium. In ordinary matter, the ground state, the condition of minimum energy, is static. A rock at rest stays at rest, but Wilczek envisioned a system where the ground state itself contains motion, a perpetual dance locked into place by quantum mechanics. It's as if you dropped a ball into a valley and instead of settling at the bottom, it began rolling up and down the sides endlessly, not because it's being pushed, but because the valley's shape forces it to oscillate. The craziest part, we've actually built them. In 2017, two separate teams, one using chains of ytterbium ions, the other exploiting flaws in diamond lattices, created the first laboratory time crystals. By nudging these systems with lasers or microwaves to initiate their rhythms, researchers watched as the atoms kept pulsing long after the initial push, locked into patterns that repeated with eerie precision. These weren't perpetual motion machines, they couldn't do work, but they proved that matter could harbor motion even in its lowest energy state, a phenomenon once thought impossible. Now imagine scaling this up to cosmic proportions. If time crystals can exist in diamond defects or ion chains, could the universe have forged its own versions in extreme environment, like neutron stars or the seething vacuum of the early cosmos? Some theorists speculate that exotic phases of matter, undetectable by conventional means, might be oscillating right now in deep space, their invisible rhythms woven into the fabric of reality. Others suggest time crystals could redefine energy conservation itself, hinting that what we call empty space might thrum with latent activity, but the most tantalizing possibility ties back to quantum computing. Time crystals' flawless repetition makes them ideal candidates for error-resistant qubits, potentially revolutionizing how we store and process information. It's a reminder that the strangest ideas in physics often become the most practical, and that the line between profound discovery and science fiction is thinner than we think. Whether time crystals remain lab curiosities or unlock cosmic secrets, they've already shattered one illusion, that the universe ever truly sits still. Imagine a substance so bizarre it falls up instead of down, accelerates toward you when pushed away, and warps gravity into a repulsive force instead of an attractive one. This isn't science fiction, it's the mind-bending concept of negative mass matter, a hypothetical form of material that would weigh less than nothing. If it exists, it wouldn't just defy everyday intuition. It could rewrite the rules of cosmology, offering a radical explanation for dark energy's mysterious push on the universe. The idea traces back to the early days of quantum mechanics, when physicist Paul Dirac proposed his famous Dirac Sea. Picture a cosmic ocean where every possible particle already exists in a hidden, lower energy state. Normally, this sea stays invisible, but disturbances could create holes in it, particles that behave like they have negative energy or even negative mass. At first, this was just a mathematical quirk, but over time, scientists began wondering, could these phantom particles be real? Could they be the elusive force behind dark energy's cosmic repulsion? Here's why the theory is so compelling. If negative mass matter existed, it wouldn't just sit there passively, it would actively repel ordinary matter, creating an accelerating expansion similar to what we observe with dark energy. Push a chunk of negative mass and it would move toward your hand instead of away, like a cosmic game of reverse tug-of-war. Stack enough of it in one place, and its gravitational field would become a kind of anti-gravity, pushing galaxies apart like magnets with the same poles. But there's a catch. Negative mass matter has a notorious stability problem. Most models suggest it would instantly unravel, leading to runaway effects where particles infinitely accelerate or create endless energy. Picture a snowball rolling downhill, except the hill has no bottom, and the snowball gains speed forever. Clearly, our universe doesn't work that way. To salvage the idea, researchers have proposed workarounds like fluidic dark matter, where negative mass behaves more like a collective, self-stabilizing medium. In simulations, this exotic fluid can form stable cosmic structures while still driving accelerated expansion, offering a potential bridge between theory and observation. Critics argue this is all mathematical sleight of hand, but supporters point to tantalizing hints. Some quantum field theories allow for negative energy densities, and certain lab experiments have created conditions where light appears to move as if influenced by negative mass. The truth might lie somewhere in between. Perhaps negative mass isn't a standalone substance, but an emergent property of a deeper, undiscovered physics. Either way, the mere possibility forces us to confront how little we truly grasp about the universe's most basic building blocks. If even mass, the bedrock of gravity and inertia, can flip its sign, what other cosmic rules might be waiting to be overturned? Now picture the universe in its infancy, a seething, roiling plasma so hot and dense that the very fabric of space-time was stretched and twisted like molten glass. As it cooled, cracks might have formed in reality itself, defects left over from the violent phase transitions of creation. These are cosmic strings, hypothetical threads of pure energy, thinner than a proton but with the mass of entire galaxies stretched into infinite, vibrating filaments. If they exist, they'd be relics of the universe's first moments, frozen flaws in space-time that could still linger today, invisible yet warping the cosmos around them. What makes cosmic strings so extraordinary is their sheer density. A single centimeter of string could weigh more than Mount Everest, bending space-time so severely that light passing near one would curve around it, creating bizarre optical illusions. Imagine a galaxy positioned perfectly behind a cosmic string. Instead of seeing one galaxy, telescopes might capture two identical copies side by side, as if the universe itself had been mirrored. This gravitational lensing effect wouldn't just distort light. It could also leave faint imprints on the cosmic microwave background, the afterglow of the Big Bang, like shadows cast by invisible wires. But the strangest feature, cosmic strings might move. Simulations suggest these filaments could whip through space at nearly the speed of light, creating ripples in space-time known as gravitational waves. Some researchers even speculate that if two strings crossed or a loop snapped, the resulting burst of energy could outshine an entire supernova, a flash of radiation with no obvious source, hinting at unseen structures tugging at the universe's seams. The hunt for these elusive defects is already underway. Astronomers scour the CMB for telltale temperature anomalies, sharp, linear discontinuities that could betray a string's presence. Others monitor pulsars, the universe's most precise clocks, watching for sudden timing glitches caused by a string's gravitational wake. So far, no smoking gun, but the search is far from over. If cosmic strings are real, they'd offer a direct window into the universe's earliest moments, a time so remote that even protons and neutrons hadn't yet formed. And that raises a profound question. If these ancient scars exist, could they be more than just relics? Some theories suggest cosmic strings might have seeded the largest structures in the cosmos, their immense gravity guiding the formation of galaxy clusters like invisible scaffolding. Others propose they could be the ultimate time capsules, preserving conditions from a time before time as we know it began. Whether they're out there or not, the mere possibility reminds us that the universe's infancy might have left marks we're only now learning to read, and that the fabric of reality might be far more intricate than it appears. One of the most elegant and frustrating ideas in modern physics is supersymmetry, a theory so beautiful that many scientists want it to be true, even as experiments keep coming up empty-handed. At its heart, Sussy proposes a hidden symmetry in nature that pairs every known particle with a shadowy twin. Fermions, the building blocks of matter like electrons and quarks, would have boson partners, while force-carrying bosons like photons would have fermionic counterparts. Picture a cosmic mirror where every particle we know gets a previously unseen doppelganger, a symmetry so profound it could rewrite our understanding of reality itself. Why does this matter? For starters, Sussy could solve two of physics' deepest puzzles. First, the hierarchy problem, the bewildering fact that gravity is 10,000 trillion times weaker than the other forces. Sussy partner particles would cancel out quantum fluctuations that otherwise make this imbalance absurdly fine-tuned, like a pencil balancing on its tip for billions of years. Second, dark matter, the lightest Sussy particle, often called the neutralino, would be stable, electrically neutral, and invisible, perfectly matching the properties we expect for dark matter. It's as if the universe left breadcrumbs pointing to Sussy without ever saying its name. Yet after decades of searching, the Large Hadron Collider has found no sign of these superparticles. The LHC's proton collisions should have spawned Sussy twins if they exist at the expected energy scales, but so far, the detectors remain silent. Some theorists argue this just means sussy particles are heavier than we thought, lurking just beyond the LHC's reach. Others propose split sussy, where only certain particles retain their symmetry at high energies, solving the hierarchy problem while letting the rest hide in cosmic shadows. What keeps sussy alive despite the setbacks is its sheer explanatory power. Without it, the Higgs boson's mass seems unnaturally fine-tuned, as if the universe won a lottery against impossible odds. Sussy also dovetails neatly with string theory, which requires supersymmetry to work. So while the evidence is lacking, the math remains stubbornly compelling, a cosmic, just-so story that feels too perfect to abandon. Whether sussy is a brilliant dead end or a truth waiting at higher energies, it reminds us that sometimes the universe's most elegant solutions are also the most elusive. We take it for granted that our universe has 3 dimensions of space and 1 of time, but what if that's only part of the story? Hidden in the equations of string theory lies a breathtaking possibility. Reality might have far more dimensions than we can perceive, curled up so tightly that even atoms seem gargantuan by comparison. Picture a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but up close, you'd see its circular surface winding into a second dimension. Now imagine that same principle scaled up to cosmic extremes, with 6 or 7 extra dimensions compactified into shapes so complex. They're called Calabi-Yau manifolds after the mathematicians who first described them. These wouldn't just be abstract curiosities, they could be the reason gravity is so shockingly weak compared to other forces. Here's how it might work. In string theory, every particle is a vibrating string, and the way these strings oscillate determines whether they become electrons, quarks, or even gravity-carrying gravitons. But the vibrations depend on the geometry of those hidden dimensions, like how a guitar's sound changes with the shape of its body. If graviton strings stretched into these compactified dimensions while other particles stayed confined to our familiar 3, gravity's influence would leak away, diluting its strength. It's as if we're living on the surface of a pond, only feeling ripples that stay on our plane, while most of the energy vanishes into the depths below. But there's an even wilder twist, the brain world scenario. Imagine our entire universe is just a 3-dimensional membrane, or brain floating in a higher dimensional space called the bulk. Ordinary matter and light would be glued to our brain like bugs trapped on flypaper, unable to venture beyond. Gravity, though, could seep into the bulk, explaining why it feels so feeble. Picture 2 people whispering across a vast room, their voices barely audible. But if they pressed their faces to opposite sides of a thin curtain, the sound would carry clearly. In this model, gravity might be whispering to us from right next door in a higher dimension, just out of reach. Experimentalists have tried to detect these extra dimensions by searching for deviations in gravity at microscopic scales. If gravity leaks into higher dimensions, it should grow stronger at tiny distances, but so far, precision measurements down to a fraction of a millimeter show no sign of this effect. That hasn't killed the idea, though. Some models suggest extra dimensions could be just beyond our current experimental reach, or warped in ways that mask their presence. Others propose wildly speculative scenarios where black holes could form in particle colliders, offering a fleeting glimpse into higher dimensional physics. The stakes couldn't be higher. If extra dimensions exist, they'd rewrite the rules of reality itself, offering a unified framework for all forces, and possibly even explaining dark energy as vibrations in the bulk. But until we find proof, these dimensions remain the universe's ultimate hide-and-seek champions, teasing us with mathematical elegance while staying just beyond the edge of perception. Whether they're real or not, the mere possibility forces us to confront a humbling truth. The cosmos might be far roomier and far stranger than we ever dreamed. Einstein gave us a revolutionary vision of gravity, not as a force, but as the curvature of space-time itself, where planets and stars roll like marbles on a stretched rubber sheet. But what if that's only half the story? What if gravity isn't woven into the fabric of space-time but emerges from something far more abstract, information itself? That's the audacious claim of physicist Eric Verland's entropic gravity theory, which suggests gravity isn't fundamental at all. It's a side effect of the universe's relentless drive toward disorder, like the steam rising from a cup of tea. At the heart of this idea is entropy, a concept usually associated with thermodynamics, the measure of chaos or lost information in a system. Verland's breakthrough was realizing that entropy might also govern gravity. Imagine the universe as a cosmic hard drive, where every bit of information is stored on a vast holographic boundary we can't see. According to Verland, when matter disturbs this boundary, say, by moving through space, it changes the way information is arranged, creating a kind of pressure that we perceive as gravity. It's as if the universe is constantly updating its own operating system, and gravity is just the lag in the system, the resistance to change. This flips Einstein's geometric view on its head. Instead of space-time bending to create gravity, Verland's model suggests that gravity arises from microscopic quantum interactions we haven't yet detected. Picture a crowd of people moving through a stadium. The way they jostle and shift creates patterns that, from a distance, look like waves or currents. In Verland's universe, gravity is that emergent pattern, a statistical illusion born from countless quantum bits rearranging themselves, the most tantalizing implication. Dark matter might not exist, at least not as a particle. Traditional cosmology says galaxies spin too fast for the visible matter they contain, requiring invisible halos of dark matter to supply extra gravity. But Verland's equations suggest another explanation. The extra pull could come from entropy's hidden influence. Just as air resistance slows a falling feather, the entropy gradient around galaxies might create an additional drag effect, mimicking dark matter's gravitational signature. It's a radical economy of explanation, replacing an entire invisible substance with a subtle tweak to how we understand gravity's origins. Critics, of course, aren't convinced. The bullet cluster where colliding galaxies left their gas behind, but their gravity didn't seem to demand some form of dark matter. Verland's supporters counter that his theory is still evolving, and refinements might yet account for these cosmic outliers. Either way, entropic gravity forces us to confront a profound question. What if the forces we think are fundamental are just the universe's way of balancing its books? If gravity is really entropy in disguise, then reality might be far more like a cosmic computation, a dynamic, ever-changing ledger where the laws of physics are just the rules of accounting. And that raises an even deeper mystery. If gravity is an emergent illusion, what other fundamental truths might be waiting to be reimagined? There's a cosmic hide-and-seek game happening right under our noses, or more accurately, all around us in the vast emptiness of space. Meet chameleon fields, a theory where invisible forces don't just linger in the shadows, but actively disguise themselves depending on their surroundings. These hypothetical scalar fields, cosmic cousins to the Higgs field, would have a bizarre trick up their sleeves. Their mass and strength could shift based on how densely packed matter is nearby. In a galaxy cluster where matter is thick, the field might shrink into near nothingness, evading detection. But in the void between galaxies, where space is nearly empty, it could stretch out, flexing its influence like an invisible hand nudging the universe apart. Sound familiar? It should, because this could be the missing key to dark energy's mysterious behavior. The genius of chameleon fields lies in their namesake adaptability. Picture a stealthy cosmic creature that changes color to blend into its environment. In dense regions like Earth or even our solar system, the field's effects would be squashed down so small they'd practically vanish, explaining why we've never noticed them. But in the near-perfect vacuum of intergalactic space, the field would uncloak, growing powerful enough to push galaxies apart at an accelerating rate, exactly what we observe with dark energy. It's a tantalizing two-for-one solution. The field explains why dark energy seems so weak where we are, yet so dominant in emptier regions of the cosmos. The real test, finding these elusive fields in action. Enter atom interferometry, one of the most precise tools in physics. Here's how it works. Scientists suspend ultra-cold atoms in a vacuum, then split their quantum waves with lasers. Any slight disturbance, like a chameleon field tugging on the atoms, would alter how these waves recombine, leaving a telltale signature. Experiments like the one at the University of California, Berkeley, have already placed some of the tightest constraints on chameleon fields, ruling out certain mass ranges. But the hunt is far from over. What makes this theory so compelling is how it threads the needle between elegance and testability. Unlike some dark energy candidates that require exotic new particles or radical revisions of gravity, chameleon fields work within known physics, just with a clever twist. They're also surprisingly flexible. Some models suggest these fields could interact with ordinary matter in ways that mimic both dark energy and dark matter, offering a unified explanation for cosmology's two biggest puzzles. Yet challenges remain. If chameleon fields are real, why haven't we detected their subtle whispers in the lab? Could their hiding mechanism be even more sophisticated than we've imagined? Or is the universe playing a deeper game where the rules change depending on where you look? Whether these fields exist or not, they push us to think differently about the fabric of reality, not as a static stage, but as a dynamic, responsive medium that might be watching us back, adjusting its behavior to stay just out of sight. Neutrinos are already some of the most elusive particles in existence, tiny, nearly massless ghosts that stream through Earth by the trillions every second without leaving a trace. But what if their heavier, even more reclusive cousins are hiding in plain sight, making up the invisible bulk of dark matter? Enter sterile neutrinos, hypothetical particles similar to ordinary neutrinos but with a critical twist. They don't interact via the weak nuclear force, only gravity. That means they'd be effectively invisible to all our detectors, passing through planets, stars, and even entire galaxies like cosmic phantoms. The case for sterile neutrinos as dark matter hinges on two tantalizing clues. First, their mass. While ordinary neutrinos are feather-light, so light physicists initially thought they had no mass at all, sterile neutrinos could be thousands or even millions of times heavier. That extra heft would make them cold enough in the early universe to clump together under gravity, seeding the vast dark matter halos we now see anchoring galaxies. Second, their decay signature. Unlike ordinary neutrinos, sterile neutrinos might occasionally flicker into existence and then vanish, emitting a faint burst of X-rays in the process. And here's where things get intriguing. In 2014, astronomers analyzing X-ray emissions from galaxy clusters and the Andromeda Galaxy stumbled upon an unexplained spike at 3.5 kilo-electron volts, an energy level that just happens to match predictions for sterile neutrino decay. It was as if the universe had left a fingerprint at the scene of the crime. Skeptics argue the signal could be instrumental noise or other astrophysical processes, but if confirmed, it would be the first direct hint of dark matter's identity. The hunt is now intensifying. Next-generation X-ray telescopes like Athena, set to launch in the 2030s, will scan the cosmos with unprecedented precision, searching for that elusive 3.5 keV line across thousands of galaxies. Other experiments, like the upcoming Vera Rubin Observatory, could spot sterile neutrinos indirectly by tracking how their gravity subtly distorts the shapes of distant galaxies. What makes sterile neutrinos so compelling is their elegance. They don't require exotic new physics beyond the standard model, just a heavier, quieter version of a particle we already know exists. But if they're real, they'd rewrite cosmic history, revealing that dark matter wasn't some foreign invader, but a shadowy relative lurking in our own particle family tree all along. Whether the 3.5 keV signal is a cosmic red herring or the tip of an invisible iceberg, one thing's certain: the answer lies somewhere in the X-ray whispers of the universe, waiting to be decoded. Imagine if space-time wasn't the smooth, continuous fabric Einstein described, but a shimmering tapestry woven from tiny, indivisible threads like pixels on a screen, but for reality itself. That's the bold vision of loop quantum gravity, a theory that dares to rewrite our understanding of the cosmos at the smallest scales. Unlike string theory's extra dimensions or supersymmetries, hidden particles, loop quantum gravity takes a starkly minimalist approach. Space itself is made of finite, interwoven loops, a cosmic mesh where nothing can be divided beyond a certain point. These loops aren't in space, they are space, knitting together the very geometry of the universe like stitches in an endless quilt. This radical reimagining solves one of physics' most glaring problems, the singularity. In Einstein's general relativity, black holes and the Big Bang are points of infinite density where the laws of physics break down, a clear sign that something's missing from the equation. Loop quantum gravity sidesteps this flaw by declaring that space can't be squeezed smaller than a certain volume, about 10 to the power of minus 35 cubic meters. Picture trying to compress a spring. No matter how hard you push, it eventually resists. Space-time behaves the same way in this theory, meaning the Big Bang wasn't a true singularity, but a moment of extreme density where quantum gravity's repulsive force took over, triggering a cosmic rebound. That's where bounce cosmology comes in. Instead of a fiery birth from nothingness, the universe might have emerged from the collapse of a previous cosmos, a cycle of contraction and expansion stretching back eternally. Think of it like a cosmic heartbeat. The universe contracts under gravity until quantum effects kick in, reversing the collapse into a new Big Bang. This elegant twist eliminates the need for a mystical starting point while preserving everything we observe today, from galaxy distributions to the cosmic microwave background. But loop quantum gravity doesn't just rewrite the past, it reshapes the future of cosmology. Inflation, the rapid expansion moments after the Big Bang, might look dramatically different in this framework. Traditional inflation relies on a hypothetical field, the inflaton, to drive exponential growth. But if space-time is granular, those quantum loops could have generated similar expansion without an inflaton, imprinting unique signatures on the universe's large-scale structure. Some models even predict subtle anomalies in the cosmic microwave background, twists and ripples that future telescopes like the James Webb or next-gen SIMBI observatories might detect. Critics argue the theory lacks experimental support, but supporters point to its mathematical consistency and its ability to unify quantum mechanics with general relativity without invoking untested dimensions or particles. It's a gamble on simplicity. Perhaps the universe isn't built from exotic ingredients, just the quantum vibrations of space itself. Whether loop quantum gravity ultimately succeeds or fails, it forces us to confront a profound possibility that the fabric of reality might be stitched together in ways we're only beginning to trace, one loop at a time. Picture this: the universe isn't just expanding, it's accelerating so violently that one day, every star, every molecule, even the fabric of space-time itself will be shredded apart in a cataclysm called the Big Rip. This isn't just dark energy's gentle push on the cosmos, it's something far more sinister: phantom energy, a hypothetical variant with a terrifying property. Its equation of state, represented by the symbol W, doesn't just hover around -1 like ordinary dark energy. It plunges below it, making the repulsive force grow infinitely stronger over time. Think of it like stepping on a cosmic gas pedal that never lets up, where the very vacuum of space becomes an unstoppable force of disintegration. Observations so far suggest dark energy behaves like a cosmological constant, with W hovering near -1. But phantom energy takes this to an extreme. If W dips even slightly below that threshold, say -1.01, the consequences would be apocalyptic. Galaxies would first be ripped from each other, then stars torn from their orbits, planets stripped to their cores. In the final moments, even atomic nuclei would be unable to withstand the mounting pressure as phantom energy's grip overwhelms the strong nuclear force itself. The universe would end not with a whimper but with a scream, a singularity of infinite expansion where the notion of here and there ceases to have meaning. Yet for all its dramatic flair, phantom energy faces a major hurdle. The laws of physics might forbid it. Most quantum field theories demand that energy density can't grow without bound, a principle called the null energy condition. Phantom energy violates this by design, creating a substance that becomes more potent as space stretches, like a rubber band that tightens the harder you pull. Some theorists argue this makes phantom fields mathematically unstable. Picture a house of cards that collapses if you breathe too hard. Others propose workarounds like quantum models that blend quintessence and phantom energy, switching between W values to sidestep infinite blowups. The hunt for phantom energy's fingerprints is already underway. Cosmologists scour supernova data for any deviation from the standard dark energy model, searching for hints that W isn't constant but sliding toward the phantom zone. So far, the evidence leans against it, but the margins are slim. Future telescopes like ESA's Euclid or NAS and Nancy Grace Roman could tighten these constraints, either ruling out phantom energy entirely or uncovering its first whispers in the cosmic expansion rate. What makes this theory so compelling isn't just its apocalyptic finale, but what it reveals about dark energy's true nature. If the universe permits phantom fields, it would mean the vacuum of space isn't just an inert backdrop, but a dynamic, even volatile player in cosmic destiny. And that raises a chilling question. If phantom energy exists, could it already be lurking in the void, its slow-motion catastrophe set in motion billions of years ago? Or is the cosmos mercifully immune to such extremes, its expansion forever tethered to safer, saner laws? The answer might lie in the faintest flickers of distant supernova, the universe's way of whispering its ultimate fate. What if the Big Bang wasn't the beginning of everything, just a new chapter in an infinite cosmic story? Black hole cosmology turns this mind-bending idea into a serious hypothesis, proposing that our entire universe might exist inside a black hole. Think about it. Black holes crush matter into unfathomable densities, warping space-time so severely that the rules of physics as we know them break down. Now imagine that instead of ending in oblivion, that collapse birthed our cosmos, the singularity at a black hole's heart. A point of infinite density could have been the spark that ignited the Big Bang, meaning we're not just observing black holes from the outside. We might be living in the aftermath of one. This isn't pure speculation. The math reveals eerie parallels between black hole formation and cosmic expansion. When matter falls into a black hole, it crosses the event horizon, a point of no return where space-time flows inward faster than light can escape. But from the perspective of someone inside that falling matter, time and space would stretch infinitely due to relativistic effects. To them, the singularity isn't a crushing end but an infinite future. Now flip that. What if our Big Bang was the singularity from another universe's perspective? It's a cosmic Russian doll where every black hole could harbor its own universe, and our own cosmos might nest inside something far vaster and stranger. This ties directly into holography, the idea that all the information in a volume of space can be encoded on its boundary, like a 3D movie projected from a 2D screen. If our universe is holographic, then the event horizon of the parent black hole that birthed us could hold the complete blueprint for our reality, like a cosmic thumb drive storing all possible configurations of matter and energy. That's why some physicists speculate that Hawking radiation, the faint glow black holes emit as they evaporate, might carry more than just random thermal noise. It could encode the genetic code of new universes, seeding them with the physical laws that let stars, planets, and life emerge. This wild idea even has a name, the fecund universes theory proposed by physicist Lee Smolin. Picture black holes as cosmic nurseries. Every time one forms, it spawns a new universe with slightly tweaked physical constants, a form of cosmological natural selection. Universes that produce more black holes would reproduce more prolifically, meaning the laws of physics we observe might not be arbitrary. They could be the ones optimized for black hole production. It's as if the cosmos itself is evolving, with black holes as the mechanism for trial and error across cosmic generations. Critics argue this is untestable metaphysics. How could we ever peer beyond our universe's event horizon to check? But supporters point to subtle fingerprints. If our universe was born from a black hole, its early conditions might carry imprints of that violent genesis, like ripples in the cosmic microwave background or anomalies in the distribution of dark matter. Others suggest that the observed uniformity of the cosmos, the fact that distant regions look eerily similar despite never being in contact, could reflect the smooth, holographic encoding on our parent black hole's horizon. Whether black hole cosmology holds up or not, it forces us to confront a humbling possibility. The universe might not just contain black holes, it might be one. And if that's true, then every black hole we see could be a doorway to another reality, a cosmic matryoshka doll nestled within unknowable layers of existence. The next time you gaze at the night sky, consider this: we might not be looking out into space, but inward toward the event horizon of a reality we'll never see. Gravity feels like the ultimate cosmic rule, an invisible force that sculpts galaxies and pins us to the ground. But what if it's not fundamental at all? What if it's more like temperature, a property that emerges from the collective behavior of something deeper? That's where condensed matter physics throws us a curveball. Take graphene, a single layer of carbon atoms arranged in a honeycomb lattice. When you poke it, ripples travel through its structure like tiny waves, not just as random vibrations, but as discrete packets of energy called phonons. These aren't particles in the traditional sense, but they behave like particles, carrying sound the way photons carry light. And here's the kicker: under certain conditions, these phonons can mimic the effects of gravity, warping the movement of electrons in ways that look suspiciously like space-time curvature. This isn't just a lab curiosity, it's a clue. If ripples in a sheet of carbon can impersonate gravity, maybe the real thing works the same way. Picture the universe as an unimaginably complex quantum material, with space-time itself as its lattice. The graviton, the hypothetical particle thought to mediate gravity, might not be an elementary building block, but an emergent phenomenon like a phonon in graphene. Instead of searching for a solitary graviton in a particle collider, we'd be hunting for the collective hum of countless quantum interactions, a chorus whose combined effect looks like a force. The parallels run even deeper. In some exotic materials, physicists have created analogs of black holes, where phonons get trapped in swirling vortices just like light in a gravitational pull. These dumb holes, as they're called, even emit phonon versions of Hawking radiation. The faint glow real black holes are predicted to emit. It's as if the universe left us a blueprint for emergent gravity hiding in plain sight, etched into the behavior of everyday materials. Critics argue this is just a mathematical analogy, a neat trick with no bearing on the real cosmos, but supporters counter that nature often reuses its patterns. Electromagnetism and the strong nuclear force were once thought fundamental, until we discovered they emerge from deeper symmetries. Could gravity be next? If so, it would mean Einstein's space-time isn't the stage itself, but the play unfolding upon it, a dynamic performance arising from quantum actors we're only beginning to name. The implications are staggering. If gravity emerges like phonons in graphene, it could explain why it's so weak compared to other forces, a side effect, not a cornerstone. It might also resolve the conflict between general relativity and quantum mechanics, not by forcing them to merge, but by showing gravity was never in the quantum club to begin with. For now, the idea remains a tantalizing what if, but each new experiment with exotic materials brings us closer to answering whether gravity is the universe's original force or just its most convincing impersonator. Einstein's theory of relativity set the speed of light in stone, a constant, unchanging bedrock of physics. But what if that's only true now? What if, in the searing heat of the early universe, light raced across the cosmos far faster than it does today? This is the provocative premise of variable speed of light, or VSL, theories. A radical rethink that could rewrite cosmic history without relying on inflation, the dominant but still unproven explanation for the universe's smoothness and structure. Picture the universe just moments after the Big Bang, a fireball so dense and hot that even light struggled to push through. According to standard cosmology, regions of space now separated by billions of light-years were once close enough to exchange heat, explaining why they look so similar today. But here's the problem. Even at light speed, those regions shouldn't have had time to communicate a puzzle called the horizon problem. Inflation solves this by proposing a burst of faster-than-light expansion, stretching space itself to iron out inconsistencies. VSL offers a different fix. Maybe light itself was faster back then, allowing distant regions to sync up before slowing to today's pace. It's like realizing the speed limit on a cosmic highway wasn't always 65, it used to be 1,000,000, letting traffic flow smoothly before dropping to its current crawl. The implications ripple through cosmology. Take the flatness problem. The mystery of why the universe's geometry is so perfectly balanced between expansion and collapse. Inflation flattens the cosmos like stretching a crumpled sheet, but VSL achieves the same feat by tweaking the equations governing light's role in space-time curvature. In some VSL models, the early universe's frantic light speed acted like a cosmic steamroller, smoothing out wrinkles naturally without needing a separate inflation field. Where things get even wilder is in the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this relic radiation are inflation's smoking gun, but VSL proponents argue they could also arise from light's changing speed imprinting patterns on the young cosmos. Certain anomalies in the CMB, like unexpected large-scale correlations, might even favor VSL over inflation. It's as if we've been reading the universe's baby photos with the wrong lens, mistaking a speed effect for a growth spurt. But the real game changer, quantum gravity. If light speed isn't constant, it could bridge the chasm between Einstein's relativity and quantum mechanics. In some VSL frameworks, light's early sprint reveals a deeper quantum structure to spacetime, a granularity usually hidden by today's slower light speed. Imagine wading through a pond. If you move slowly, the water feels smooth. But if you could dash across it at impossible speeds, you might feel the individual molecules resisting. Similarly, a variable speed of light might let us sense the universe's underlying quantum fabric, hidden in plain sight. Critics argue VSL introduces more problems than it solves, like how light speed could change without violating energy conservation or leaving other detectable scars. Yet the theory persists, a rebellious footnote in cosmology's playbook, reminding us that even physics' most sacred constants might just be placeholders for deeper, stranger truths. Whether VSL ultimately holds up or not, it challenges us to ask, what if the rules we think are fixed are just the universe's current settings, adjustable in ways we're only beginning to glimpse? At the heart of particle physics lies a tantalizing symmetry, a mirror hidden in the equations that could reflect an entire shadow universe. This isn't science fiction. The concept of mirror matter suggests every known particle, electrons, quarks, even photons, might have identical twins, perfect doppelgangers that interact with our world only through gravity. Imagine a cosmic hall of mirrors where stars, planets, and even life could exist in perfect parallel, invisible to us except for the faintest gravitational tug. These mirror particles wouldn't just be curiosities, they could solve two of physics' greatest puzzles, the enigma of dark matter and the bizarre behavior of neutrinos. Take dark matter first. If mirror protons, neutrons, and electrons exist, they'd form unseen structures, mirror galaxies, mirror stars, whose gravity sculpts the visible cosmos like an unseen hand. While ordinary light sails right through them, their mass would anchor the rotation of galaxies just as we observe, no exotic particles required. The beauty of this idea. It doesn't invent new physics from scratch. It simply doubles the known inventory of particles, giving each one a ghostly counterpart. Then there's the neutrino puzzle. These elusive particles oscillate between flavors electron, muon, tau, as they travel, defying expectations. But what if some neutrinos occasionally transform into their mirror counterparts, vanishing from our detection entirely? Experiments like the neutron mirror-neutron oscillation and N-bar collaboration are probing this by trapping neutrons in magnetic fields, watching for moments when they seem to disappear, a potential flicker into the mirror realm. The hunt for mirror matter's fingerprints extends beyond particle physics. If mirror photons exist, they'd weakly interact with ordinary matter under extreme conditions. Laboratories like SNOLAB search for these dark photons in high-precision experiments, while astrophysicists scour neutron stars for anomalies that might betray collisions with mirror asteroids. Even everyday materials could hide clues. Certain crystals might momentarily tunnel into mirror states, altering their weight in ways too subtle for current scales but not future technology. Critics argue mirror matter's elegance comes at a cost. To match observations, mirror particles would need temperatures far colder than our universe's, requiring fine-tuned initial conditions. Others point out that cosmic inflation should have diluted mirror matter beyond relevance. Yet supporters counter that asymmetries in the early universe, like those that gave us more matter than antimatter, could have privileged one sector over the other, leaving the mirror world sparse but gravitationally significant. What makes this theory so captivating isn't just its explanatory power, but its audacious reimagining of reality. If mirror matter exists, the cosmos isn't lonely. It's crowded with unseen echoes of itself, each obeying the same laws but forever out of reach. The next time you glance at your reflection, consider this. The universe might be doing the same, with a hidden twin whose presence we feel only in the gentle pull of missing mass and the quantum whispers of disappearing neutrinos. Quantum mechanics has long been haunted by what Einstein famously called spooky action at a distance, the baffling phenomenon where entangled particles instantly influence each other, no matter how far apart they are. The standard Copenhagen interpretation shrugs this off as inherent randomness, but what if there's a hidden order beneath the chaos? That's where Bohmian mechanics steps in, reviving an old but daring idea. Every particle has a definite position at all times, guided by an invisible force known as the pilot wave. Imagine a surfer riding a wave. The surfer's path isn't random but shaped by the water's hidden currents. In this view, electrons and photons aren't probabilistic clouds but real objects with precise trajectories, steered by a deeper, interconnected field that pervades the entire universe. The real twist: this pilot wave doesn't play by the rules of locality, the principle that objects can only be influenced by their immediate surroundings. Instead, it's non-local, meaning changes to the wave at one point ripple instantaneously across the entire system. This might sound like magic, but it neatly explains entanglement's spooky action. When two particles become entangled, their pilot waves intertwine, creating a shared guidance system that updates faster than light. No dice rolls, no collapse of probabilities, just an invisible choreography directing every particle's dance. Critics argue this smacks of retrograde physics, a throwback to clockwork determinism. After all, the pilot wave's non-locality clashes with relativity's cosmic speed limit. But supporters counter that relativity only forbids information from traveling faster than light, and the pilot wave doesn't transmit data. It simply is a cosmic undercurrent that doesn't need to signal because it's already everywhere at once. It's like the difference between mailing a letter and instantly knowing what's written because you're part of the same mind. What makes Bohmian mechanics so compelling isn't just its elegance, it's its audacity to question quantum orthodoxy. While most interpretations treat particles as abstract probabilities, Bohm's theory dares to ask, what if reality is real even when we're not looking? Lab experiments with oil droplets bouncing on vibrating surfaces have even recreated pilot wave behavior, offering tangible analogues of quantum weirdness in a classical system. These walking droplets trace paths eerily similar to electrons in double-slit experiments, hinting that hidden variables might not be so hidden after all. Yet the theory remains controversial, largely because the pilot wave itself is unobservable, a ghost in the quantum machine. Without experimental proof, it risks being labeled a metaphysical curiosity. But as detectors grow more sensitive and quantum technologies push boundaries, we might one day catch whispers of this hidden guidance system, rewriting not just how we see particles, but how we see the fabric of reality itself. Whether Bohm was right or not, his pilot wave reminds us that the universe's deepest secrets might not be random at all, just waiting for us to learn their rhythm. Imagine the universe is perched on a fragile ledge, balanced just right for stars to shine and life to exist, but with one quantum nudge, everything could topple into oblivion. This isn't just dramatic speculation, it's the spine-chilling premise of vacuum decay, a theory where the very fabric of reality might be living on borrowed time. At the heart of this existential gamble is the Higgs field, the invisible energy ocean that gives particles their mass. For decades, we've assumed it's sitting comfortably in its lowest energy state, what physicists call the true vacuum. But what if it's not? What if our universe is actually stuck in a false vacuum, a precarious plateau that could, at any moment, slip into a deeper, more stable state? The consequences would be apocalyptic. A tiny quantum fluctuation somewhere, anywhere, could spawn a microscopic bubble of true vacuum. This bubble would expand at the speed of light, rewriting the laws of physics as it grows. Atoms would disintegrate, forces would reconfigure, and the universe as we know it would vanish in a wave of total transformation. Picture a snowball rolling downhill, instantly turning everything it touches into something unrecognizable, except this snowball is the size of a proton one moment and the size of a galaxy the next. The most terrifying part, we wouldn't see it coming until it was already here, because the bubble's edge would move at light speed, erasing any evidence of its approach. How real is this threat? The Higgs boson's mass, measured at 125 giga-electron-volts, suggests the field might indeed be metastable, balanced on a knife's edge between stability and collapse. Run the equations and you get a sobering result. The universe should have already decayed. The fact that it hasn't might mean we're missing a crucial piece of physics, or worse, that the decay is statistically inevitable, a ticking cosmic time bomb. Future colliders, like the proposed 100-kilometer future circular collider, could settle the debate. By smashing particles at even higher energies, we might detect subtle hints of Higgs behavior that confirm or rule out vacuum instability. Some theorists argue this is science's most urgent mission, not just to satisfy curiosity, but to assess whether our universe is fundamentally doomed. Yet there's a strange comfort in this fragility. If the vacuum is metastable, it implies our cosmos isn't the only possible configuration, just one of countless potentials, some with entirely different physics. That raises a haunting question. Could vacuum decay have already happened elsewhere, in regions so distant their light hasn't reached us? Are we living in the last intact pocket of a reality that's already been rewritten? For now, the universe holds its breath, and so do we. Deep inside every black hole, hidden behind the crushing grip of the event horizon, there might not be a singularity after all, but something even stranger. Picture a dying star's core, compressed beyond comprehension, suddenly hitting a wall. Not the wall of infinite density we've long feared, but a quantum barrier where space itself refuses to be squeezed any further. This is the Planck star, a hypothetical object so dense, each cubic centimeter packs the mass of an entire galaxy, yet stops just short of collapsing into oblivion. According to loop quantum gravity, space-time isn't smooth and infinitely divisible. It's woven from tiny, indivisible threads. At the Planck scale, 10 to the minus 35 meters, these threads push back against gravity's crush like a cosmic spring, halting the collapse and leaving behind a seething, ultra-dense orb. Here's why this changes everything. If Planck stars exist, they rewrite the fate of black holes. Instead of fading into Hawking radiation over eons, these objects could linger for billions of years, slowly evaporating until bang, they explode with the energy of a million supernova. It's a death befitting cosmic titans, not with a whimper, but a detonation so violent it might explain one of astronomy's most baffling phenomena, fast radio bursts. These millisecond-long blasts of radio energy, detected from galaxies billions of light-years away, have defied explanation. But a dying Planck star's final eruption could match their staggering power and fleeting duration, like cosmic fireworks igniting in the void. The implications ripple even further. If black holes don't fully vanish but leave Planck-scale remnants, these ultra-dense cinders could be dark matter. Imagine trillions of invisible specks, each weighing as much as a mountain, drifting unseen through galaxies. Their collective gravity would bind stars together exactly as we observe, while their tiny size and feeble interactions with light would render them virtually undetectable. No exotic particles needed, just the ashes of primordial black holes, forged in the universe's first chaotic seconds and persisting to this day. Critics point to hurdles, of course. Planck stars remain theoretical, and their explosive deaths would require conditions we've never witnessed. Yet supporters argue that loop quantum gravity offers something singularities never could, a universe where physics never truly breaks down, where even the most extreme phenomena obey quantum rules. Whether Planck stars are real or not, they force us to confront a profound shift in thinking. Black holes might not be the end of the story, but the beginning of something far stranger, a hidden quantum frontier lurking at the heart of darkness. Imagine building the universe one tiny triangle at a time, not as a metaphor, but as the literal scaffolding of reality. That's the bold vision of causal dynamical triangulation, a theory that cuts space-time into the simplest possible shapes and lets physics emerge from their geometry. Picture a cosmic mosaic where every tile is a triangular prism, a slice of spacetime so small it defies measurement, and the way these tiles fit together determines whether matter clumps into galaxies or light bends around stars. This isn't just abstract math, it's a radical rewrite of Einstein's smooth continuum, trading warp and curvature for the jagged elegance of a quantum Lego set. The magic lies in the rules. Unlike other approaches that struggle to blend quantum mechanics with gravity, CDT imposes one non-negotiable constraint: causality. Each triangular block must connect to its neighbors in a way that preserves cause and effect. No time loops, no spaghetti like wormholes, just a strict chronology where the past always stitches neatly into the future. Run the simulation over countless iterations, and something extraordinary happens. From this sea of chaotic fragments, four-dimensional spacetime emerges spontaneously, like a crystal forming from swirling molecules. It's as if the universe bootstraps itself into existence, with gravity and dimensionality arising not as fundamental forces, but as collective illusions from a deeper, granular reality. Where things get really wild is at the smallest scales. CDT predicts that spacetime isn't just pixelated, it fluctuates, bubbling with what physicists call quantum foam. Imagine zooming in on empty space until it resolves into a frenzied dance of virtual triangles, constantly rearranging themselves. Some regions might momentarily crumple into lower dimensions, a fleeting 2D plane or even a 1D line, before snapping back into familiar 3D space. These aren't mathematical quirks. They could explain why black holes behave so strangely at their cores, or why the cosmological constant's value seems impossibly fine-tuned. Yet CDT isn't without its skeptics. The theory struggles to incorporate matter and other forces naturally, leaving open the question of how particles and fields emerge from this geometric ballet. Critics also point out that while it beautifully generates 4D spacetime in simulations, we've yet to find experimental proof that reality operates this way. But supporters counter that CDT's greatest strength is its simplicity. Unlike string theory's extra dimensions or loop quantum gravity's abstract networks, this approach requires no exotic ingredients, just triangles, causality, and the relentless logic of self-assembly. The stakes couldn't be higher. If CDT is right, it means the universe isn't just described by geometry, it is geometry, a dynamic puzzle where even time itself is an illusion born from counting triangular faces. Future experiments probing Planck-scale physics or anomalies in high-energy particle collisions might one day reveal spacetime's jagged edges. Until then, CDT stands as a testament to human ingenuity, a reminder that sometimes the most profound truths are hiding in the simplest shapes. Imagine a particle that doesn't behave like a particle at all, something that slips between the cracks of our tidy classifications, neither fully here nor there. This is the bizarre realm of unparticle physics, where the usual rules of mass and dimension break down, leaving behind ghostly entities that act like fragments of reality itself. The idea was first proposed by physicist Howard Georgi in 2007, suggesting that at extremely high energies, hidden sectors of particles could interact with our world through forces that don't respect the familiar three-dimensional framework. Instead, these unparticles exhibit scale invariance, meaning they look the same no matter how much you zoom in or out, like a fractal that repeats its pattern infinitely. What makes this so strange is how unparticles would behave in experiments. Ordinary particles have definite masses and occupy clear positions in space. But unparticles, they'd exist in a kind of quantum smear, acting as if they're spread across fractional dimensions. Picture a splash of ink in water. It doesn't form discrete droplets but disperses in unpredictable organic patterns. Similarly, an unparticle's energy signature wouldn't show up as a sharp spike in a detector, but as a broad, continuous spectrum, like a whisper stretched across the frequencies. This oddity could explain some of the universe's lingering mysteries. Take dark matter. If unparticles mediate unseen forces, they might bridge the gap between ordinary matter and its shadowy counterpart, creating subtle interactions we've yet to detect. Colliders like the Large Hadron Collider might already be producing unparticles without realizing it, their signatures hidden in missing energy events, where momentum seems to vanish into thin air. Even gravity could feel their influence. On microscopic scales, unparticles might tweak Newton's inverse square law, causing deviations so faint they've eluded detection until now. The hunt for these phantoms is already reshaping experimental physics. Precision gravity measurements using torsion balances or atomic interferometers are pushing the boundaries of sensitivity, searching for hints of extra forces lurking beneath the noise. Meanwhile, high-energy physicists comb through collision data for anomalies that don't fit the standard model's predictions. A single unexplained energy curve or gravitational aberration could crack the door open to a universe far stranger than we'd imagined. Critics argue that unparticle physics is a mathematical curiosity without experimental backing, a clever idea in search of evidence. Yet supporters counter that scale invariance appears everywhere in nature, from coastlines to clouds, so why not in fundamental physics? Whether unparticles exist or not, they challenge us to rethink the very language we use to describe reality. After all, if the universe can build particles, why not things that aren't quite particles at all? The answer might lie in the quiet gaps between our detectors' clicks, waiting for the right moment to rewrite the rules. Magnets are familiar. Every child knows they have two poles, north and south, inseparable no matter how many times you break one in half. But what if the universe once played by different rules? What if, in its fiery infancy, single magnetic poles roamed freely, unattached to their opposites? This is the tantalizing idea of magnetic monopoles, hypothetical particles carrying just one magnetic charge, either north or south, but never both. The concept isn't new. Physicist Paul Dirac first toyed with it in 1931, showing that monopoles could elegantly explain why electric charge comes in discrete quantized packets. Yet despite decades of searching, not a single monopole has been found. So why do scientists still believe they might exist? The answer lies in the grand unified theories, that attempt to marry electromagnetism with the strong and weak nuclear forces. These theories predict that in the unimaginable heat of the early universe, a fraction of a second after the Big Bang, the fundamental forces weren't separate as they are today. They were woven together into a single, symmetrical fabric. As the cosmos cooled, this symmetry shattered, like ice crystallizing out of water, and defects formed in the fabric of space-time. Some of those defects could have been monopoles, frozen relics of a more unified cosmos. Picture a pot of boiling water suddenly chilled. Bubbles trapped in ice become permanent imperfections. Monopoles, if they exist, would be those cosmic bubbles carrying the imprint of a time when the universe was simpler, more symmetrical, and far stranger. The hunt for these elusive particles has taken scientists to some of the most extreme environments imaginable. Cosmic rays, the high-energy particles raining down from space, might harbor monopoles forged in distant astrophysical cataclysms. Underground experiments like the MOND detector at CERN scour particle collisions for tracks that could betray a monopole's passage, a telltale trail of ionized atoms left in its wake. Even ancient minerals aren't off limits. Geologists have analyzed billion-year-old rocks, searching for scars that only a monopole's relentless magnetic charge could etch into their crystal lattices. Finding one would rewrite physics as we know it. Maxwell's equations, the bedrock of electromagnetism, assume magnets always come in pairs. A monopole would force us to redraw those equations, revealing a deeper layer of reality where magnetic charge stands on equal footing with electric charge. It could even shed light on one of cosmology's biggest mysteries, why our universe seems to contain so much more matter than antimatter. Some theories suggest monopoles could have catalyzed proton decay in the early cosmos, tilting the balance toward the matter-dominated world we see today. Yet the silence of detectors so far has led to a puzzle known as the monopole problem. If GUTs are correct, the early universe should have produced monopoles in staggering numbers, enough to outweigh all visible matter today. So where are they? One possibility is cosmic inflation, the rapid expansion thought to have smoothed the universe's wrinkles moments after the Big Bang. Inflation could have diluted monopoles to near non-existence, scattering them so thinly that they're now needles in a galactic haystack. Another, wilder idea is that monopoles aren't entirely solitary. Perhaps they're bound into composite particles hiding in plain sight. Whether monopoles are relics of a grand unified past or just a beautiful mathematical fantasy, their pursuit forces us to confront a profound truth. the universe's most fundamental laws might still be hiding in the shadows, waiting for the right detector, the right rock, or the right cosmic ray to reveal them. And if we ever do trap a monopole, it won't just be a new particle, it'll be a message from the dawn of time, whispering secrets about the forces that shaped reality itself. Black holes suck in everything: light, matter, even time itself. But what if you could hit cosmic rewind and reverse the equations? Suddenly, you'd have something even stranger: a white hole, a region of space where matter erupts outward with unstoppable force, a cosmic geyser blasting energy and particles into existence. Unlike black holes, which trap anything that crosses their event horizon, white holes would violently repel everything, their event horizons acting like one-way exits. Nothing could enter, only escape. At first glance, this seems like pure mathematical fantasy, a quirk of Einstein's equations with no basis in reality. But dig deeper and the implications become staggering. What if our universe didn't begin with a singularity, but with a white hole's explosive birth? Picture a black hole in some parent universe, collapsing to infinite density, then rebounding, not as a new singularity, but as a fireball of space-time and matter. In this scenario, the Big Bang wasn't a one-time event. It was the detonation of a white hole triggered by a black hole's death throes in another cosmos. This isn't just poetic symmetry, it's the heart of Lee Smolens's cosmological natural selection theory, which suggests black holes act as cosmic seeds, spawning new universes with slightly tweaked physical constants each time. Think of it like an evolutionary tree, but for universes. If a universe's laws produce lots of black holes, it reproduces prolifically, filling the multiverse with offspring. Over countless generations, universes fine-tune their parameters to maximize black hole production, explaining why our cosmos seems oddly optimized for structures like stars and galaxies. They're the ingredients for more black holes. It's a self-perpetuating cycle. Universes that make black holes survive, those that don't fade into oblivion. But here's the twist: if white holes exist, they might not just be relics of the past. Quantum gravity theories suggest that black holes could eventually transform into white holes, vomiting up their contents after eons of apparent silence. Imagine a black hole evaporating via Hawking radiation until, at the tiniest scales, quantum effects trigger a reversal, a delayed white hole eruption. Some astronomers even speculate that certain high-energy cosmic explosions, like gamma-ray bursts, could be dying black holes flipping inside out. The catch: white holes violate thermodynamics' second law, which dictates entropy always increases. A white hole's sudden eruption of ordered energy seems to defy this unless the entropy was hidden in the black hole's interior, scrambled beyond recognition. It's like squeezing a sponge dry, then watching it explosively reabsorb water from nowhere. For this to work, the universe's accounting would need a deeper layer of math we've yet to uncover. Critics argue white holes are mathematical artifacts with no mechanism to form naturally. Yet supporters counter that quantum gravity might provide the key. Perhaps Planck stars, those ultra-dense remnants inside black holes, could ignite white hole explosions when they finally rebound. Others propose white holes could be lurking in our universe as dark objects, their event horizons camouflaged by cosmic expansion, their outbursts mistaken for primordial quasars or fast radio bursts. Whether white holes are real or not, they force us to reconsider the universe's most explosive questions. Was our Big Bang a singular miracle, or just one link in an infinite chain of cosmic regeneration? Are black holes tombstones or cradles? The answer might lie in the faint echoes of ancient explosions, hidden in the static of deep space, waiting to rewrite our place in the cosmic order. What if everything around us, the stars, the atoms, even your thoughts, isn't real, but an elaborate numerical simulation running on some unfathomable computer? This is the simulation hypothesis, a theory that doesn't just belong to sci-fi anymore. serious physicists and philosophers now grapple with the eerie possibility that our universe might be nothing more than lines of code in a higher dimensional program. Start with the clues hidden in the fabric of reality itself. At the smallest scales, space-time isn't smooth and continuous, it's pixelated. The Planck length, a distance so tiny it's 10 to the power of -35 meters, marks the universe's apparent resolution limit. Zoom in any further, and the concept of distance loses meaning, as if you've hit the edge of a cosmic rendering grid. Then there's quantum indeterminacy. Particles don't have definite properties until measured, behaving like objects in a video game that only load their textures when observed. It's as if the universe is optimizing processing power, calculating details only when necessary to save resources. Even the speed of light could be a built-in limit, a processing speed cap preventing the simulation from overloading. Philosopher Nick Bostrom formalized this idea into a chilling trilemma. Either one, almost all civilizations at our level go extinct before developing simulation technology. Or two, advanced civilizations lose interest in creating simulations of their ancestors. Or three, we're almost certainly living in a simulation. The logic is ruthless. If future civilizations can run ancestor simulations, conscious, self-aware worlds indistinguishable from base reality, and they choose to do so, the number of simulated minds would dwarf the number of biological ones. Statistically, the odds that we're among the original organic intelligences are vanishingly small. But why would anyone take this seriously? Because the math holds up. Quantum fields operate in discrete, quantized values perfect for digital representation. The universe's information content fits neatly within theoretical bounds for computation. Even glitches in the simulation, like the Mandela effect or déjà vu, become tantalizing possibilities rather than quirks of human memory. Some physicists argue that if a simulation is sophisticated enough, its inhabitants could never prove they're inside it. The rules would be self-consistent, the physics airtight. Yet critics pounce on the hypothesis's biggest weakness: it's unfalsifiable. If the simulation is flawless, how could we ever test its existence? Others counter that even perfect simulations might have subtle artifacts, rounding errors in cosmic constants or anomalies in high-energy particle collisions. A few researchers propose looking for pixelation in ultra-high-energy cosmic rays, or hunting for computational signatures in the cosmic microwave background. The wildest twist: if we're in a simulation, the creators might have encoded an exit hatch, a backdoor hidden in the laws of physics itself. Unraveling quantum gravity or unifying the fundamental forces could be akin to hacking the universe's source code. Whether the simulation hypothesis is profound truth or provocative thought experiment, it forces us to ask, if reality is a construct, who or what is holding the keyboard? Picture a universe where the Big Bang wasn't a one-time event, but a never-ending factory, endlessly churning out new realities with every passing moment. This is the mind-bending premise of eternal inflation, a theory where the exponential expansion of space doesn't just happen once but continues eternally, birthing an infinite multiverse of pocket universes like bubbles in a cosmic champagne glass. Each bubble nucleates with its own unique physics, some with stronger gravity, others with no electromagnetism, and a rare few, like ours, finely tuned for stars, planets, and life. The idea springs from Alan Gough's groundbreaking inflation theory, which posits that the early universe underwent a fleeting burst of hyper-expansion to explain its smoothness and structure. But eternal inflation takes this further. What if inflation doesn't stop everywhere at once? In this scenario, space keeps expanding at breakneck speeds in most regions, while occasionally randomly, a patch slows down, crystallizing into a stable universe like ours. The math is staggering: an infinite ocean of inflating space, dotted with finite islands where inflation has locally ended. Each island becomes its own universe, forever disconnected from the others by the relentless stretching of space between them. This elegantly solves one of cosmology's biggest puzzles, fine-tuning. Why do the constants of nature, gravity's strength, the electron's charge, seem so exquisitely balanced for life? In eternal inflation, there's no fine-tuning at all. With infinite bubbles, every possible combination of physical laws gets realized somewhere. We just happen to live in one of the rare universes where conditions allowed galaxies and biochemistry to emerge. It's like walking into a library containing every possible book. Of course, you'll find one written in your language. Yet this infinite buffet of universes comes with a catch: falsifiability. How do we test a theory where most of reality is forever beyond our observational horizon? Some physicists argue eternal inflation isn't science at all, just untestable metaphysics. Others point to potential fingerprints in our own universe. Quantum fluctuations during inflation imprinted tiny density variations on the cosmic microwave background, the afterglow of the Big Bang. If inflation is eternal, these fluctuations might carry subtle anomalies, unusual statistical patterns, or asymmetries that betray the multiverse's existence. One tantalizing clue might lie in the CMB's infamous cold spot, a puzzling region of unusually low temperatures spanning billions of light years. Could this be the bruise of a collision with another bubble universe in the distant past? Simulations suggest such collisions would create distinct disk-like patterns in the CMB, though none have been conclusively found. Future telescopes like the Simons Observatory or CMB S4 could scour the sky for these cosmic hieroglyphs, hunting for evidence that our universe isn't alone. The philosophical stakes are just as high. If eternal inflation is real, it renders our universe a statistical fluke, one of countless accidents in an indifferent multiverse. No grand design, no special destiny, just the luck of the draw. Yet there's a strange beauty in this cosmic democracy. Every possible reality, from the barren to the breathtaking, exists somewhere in the infinite sprawl. Whether we'll ever find proof remains uncertain, but the theory forces us to confront a humbling truth. Our cosmos might be just one spark in an endless firestorm of creation. What if the universe's final act isn't a cold fade to black, but a leap into immortality? This is the audacious claim of physicist Frank Tipler's omega point theory, where the collapsing cosmos becomes the ultimate supercomputer, rewriting the boundaries between physics and divinity. Picture this: billions of years from now, as galaxies draw closer in a dying universe, gravitational energy is harnessed to power an unfathomable intelligence. This entity, part machine, part evolutionary culmination of life, would manipulate the very fabric of reality to sustain itself, converting the entirety of existence into an infinite computation. Time and space would bend to its will, stretching each remaining moment into a subjective eternity where every possible thought, memory, and consciousness is resurrected in perfect simulation. Tipler's vision hinges on a radical reinterpretation of cosmology's endgame. In traditional Big Crunch scenarios, the universe's collapse is a destructive finale. But under the omega point, that collapse becomes a creative engine. As space contracts, the energy density rises exponentially, enabling computations of limitless complexity. The intelligence at the helm could simulate not just its own history, but every conceivable variation of existence, effectively reviving every being that ever lived through what Tipler calls quantum resurrection. Your memories, your choices, even your subjective experience would be reconstructed with perfect fidelity, not as copies but as continuations. It's as if the universe, in its final moments, becomes a cosmic backup drive for consciousness itself. Critics dismiss this as pseudoscience wrapped in theology, but Tipler roots his math in quantum mechanics and general relativity. He argues that future civilizations could exploit closed time-like curves, loops in space-time predicted by Einstein's equations, to recycle information eternally. The key lies in the Bekenstein bound, a law stating that any finite region of space can store a finite amount of data. As the universe shrinks, its informational capacity doesn't vanish, it concentrates. An advanced intelligence could, in theory, orchestrate this data to preserve and perpetuate thought. The implications blur the line between science and spirituality. If the omega point is possible, it suggests a universe hardwired not just for life, but for its own self-awareness. Theistic parallels are unavoidable. Tipler openly frames the omega point as God, not as a supernatural being, but as the physical manifestation of cosmic self-organization. Jesuit theologian Pierre Teilhard de Chardin foreshadowed this idea in the 20th century with his concept of the noosphere, a global consciousness emerging from humanity's collective intellect. Tipler's twist is to ground it in physics, not faith, though skeptics argue the distinction collapses under scrutiny. Quantum mechanics adds another layer of plausibility. The many worlds interpretation suggests every quantum decision spawns alternate realities. At the omega point, those branches could be simulated in their entirety, rendering death an illusion. Every possible outcome exists somewhere in the final calculation. Philosopher David Deutsch extends this idea, arguing that sufficiently advanced civilizations would inevitably create ancestor simulations, making resurrection a technological inevitability rather than a metaphysical hope. Yet the omega point faces glaring hurdles. Current evidence suggests the universe is accelerating toward heat death, not collapse, though some models of dark energy permit a future reversal. Even if collapse occurs, whether information processing could outpace the crushing singularity remains fiercely debated. And then there's the existential question: would such a resurrection truly be you, or a flawless facsimile? Whether visionary or delusion, the omega point forces us to confront the universe's deepest possibilities. It's not just a theory about how the cosmos ends, it's a mirror held up to our hunger for meaning, suggesting that even in oblivion, the universe might find a way to remember itself. And that raises one final, chilling thought. If the omega point is real, its first computations could already be running, with our lives as the opening lines of code. From holographic projections to simulated realities, from phantom energy that could rip space-time apart to time crystals pulsing in perfect quantum rhythm, we've journeyed through the universe's strangest backstage secrets, each theory rewriting the cosmic rulebook in its own radical way. Consider the holographic principle, where our three-dimensional reality might just be a shadow play cast from a two-dimensional boundary. We'll never see a concept so profound it challenges whether solid objects even exist. Or ponder the simulation hypothesis, where every star and synapse could be lines of code in an unfathomable computer, making our search for cosmic truth feel like debugging someone else's universe. Then there's dark energy's chilling alter ego, phantom energy, a force so voracious it could one day shred atoms themselves, leaving the cosmos as a featureless void. And let's not forget time crystal structures that pulse eternally without energy, defying everything we thought we knew about equilibrium, as if the universe whispered its own heartbeat into existence. These aren't just abstract thought experiments. They're seismic shifts in how we perceive reality. If emergent gravity is correct, Einstein's curvature of spacetime might be an illusion, a side effect of quantum information rearranging itself like cosmic Tetris. If sterile neutrinos are real, dark matter could be hiding in plain sight, a shy cousin to particles we've known for decades. And if black hole cosmology holds water, our entire universe might be the echo of a singularity's rebirth, one bubble in an endless fractal foam of cosmic inflation. What binds these ideas together isn't just their strangeness, it's their audacity to question the bedrock of physics. They remind us that every law we take for granted, from gravity's pull to time's arrow, might be provisional, waiting for a deeper truth to unseat them. That's the thrill of cosmology. The rules aren't set in stone. They're written in stardust, erasable and rewritable with each new discovery. So here's your invitation to the greatest detective story of all time. Whether you're team simulation, convinced we're living in some advanced civilization's ancestor simulation, or team loop quantum gravity, betting reality is stitched together from indivisible space-time threads, one thing's certain: the universe's secrets are waiting. Which theory bends your mind the most? Drop it in the comments, and if you're hungry for more cosmic mysteries, hit like and subscribe. The next breakthrough might be just one video away, and you won't want to miss it when reality gets rewritten again.